Okay, so this is just a video recap of Module 4 with multiple linear regression. So the term multiple linear regression just means that you're adding multiple predictors to your model. So in some sense, when you go over Module 4, right, you want to link back with what you've seen in Modules 1, 2, and 3 with simple linear regression because so the general ideas are similar, right? There are just some minor differences in interpretation. So the first thing I'll mention is be careful when you read other books or websites from a notational perspective. So in our textbook, they use the letter K to denote the number of predictors in the multiple linear regression model. And so far, we are assuming only first order additive models. That means these are basically models of the following form where each term, right, has its own coefficient, and we add that coefficient to the model. Later on, we'll be looking at other kind of models, but it's basically this framework, right? So in this case, right, K will denote the number of predictors here, and P is the number of parameters in your model. And in the case of only first order additive models, then this value of P is equal to K plus 1, right? Because you have K coefficients for the K predictors plus 1 intercept term. So that's how our book writes it, and I've tried to be as consistent with the notation that I've used in my notes as well. Now, in some other books or resources, they use P to denote the number of predictors and K to denote the number of parameters. So they might switch it the other way around. So just be aware of that. One recommendation I have is to actually think in terms of number of parameters, because in later modules we will look at other models, not just the first order additive models, because in those models this relationship no longer holds. So it's best to, in my opinion, to view it in terms of number of parameters P. Some comparison with simple and multiple linear regression. If you compare formulas between the two, you realize that formulas for simple linear regression is the same as multiple linear regression when you set P equals to 2 or K equals 1. So you can just compare these two and make other similar comparisons. To assess if regression assumptions are met, we will use a residual plot. In this case, though, with the residual plot with multiple linear regression needs to have the response on the y-axis and the fitted values has to be on the x-axis, and you can't use a scatter plot, right, of the response versus the predictors because you have multiple predictors. The key of differences are actually in interpretations of the coefficients, and so we'll go over these differences. I kind of put here minor in quotes. They may seem minor, but in my opinion, practically speaking, they do have pretty important implications. So there's this article, if you go through the notes, you can click the link on this hyperlink over here. It's about sleep and college students. And there's a statement or this paragraph in the article, right? The study at the University of St. Thomas found that for each additional day of sleep disturbance, so this kind of sounds like a slope interpretation, right? As you increase your x variable by 1, right? So this number of days of sleep disturbance sounds like it's the predictor. College students experience the likelihood, right, of dropping across rows by 10%. So it kind of looks like that's the response variable. And then they also had another response variable, the GPA. So this statement right over here sounds like an interpretation of a slope. But with multiple predictors, you notice that there's this additional statement over here where most other factors known to influence academic success were taken into account. So when I read a statement like this, and if you actually go back to the link and take a look at the study in detail, you'll realize they did use a multiple linear regression a model over here. So what this statement means is that if you're comparing students where these other factors, so maybe other factors could be, incoming GPA, right? What are the factors known to influence academic success? So maybe incoming GPA, socioeconomic status, and I'm just listing 2 of them, right? But if you're comparing students who have similar values of incoming GPAs and economic status, right? Then for those students, right, for every additional day of sleep disturbance, then the likelihood of dropping across rose by 10%. So this bolded statement is key because it's explicitly saying, right, that you're comparing students with who are similar in all these other factors. So these other factors, so that you can see how the impact of sleep disturbance has on the response variable, right? That it is, so one could say that, oh yeah, there is this association, right? And the association is not due to GPA or socioeconomic status. Other ways of stating the bolded statement. So the textbook way is this first bullet point. Some other very common ways that people say when controlling for the effect of other predictors. Some people will say after adjusting for the effect of other predictors. That's, I'm not such a huge fan of that, because in some instances the word adjusting has a different meaning. So I don't recommend using that, but some people do use the word adjusting, right? But it's basically saying comparing people with the same values of the other predictors. And if you look at the textbook interpretation, right, expected change in the response, but unit change in the predictor when all the others are held constant. Let's take a look at interpretation of some of the hypothesis tests in multiple linear regression. So in ANOVA tests, the ANOVA F test, the null is saying all your slopes for all your predictors are 0. In words, our model is not useful in predicting the response, right? Because if all the predictors are 0, right, it's basically saying your model is useless. The alternative is saying at least one of these is not 0. And in words, you could say your model is useful in predicting the response. Another way of thinking about these two statements, right, the null could be saying that you're considering the intercept only model, and the alternative is saying we are looking at our model, right? So the null alternative is basically saying comparing between our model versus an intercept, our model versus an intercept only model, right? So how does the null hypothesis simplify in simple linear regression, right? In simple linear regression, you only have one predictor, so that's why in simple linear regression, right, this was how the ANOVA F test was simplified. I kind of wrote an opinion over here that this ANOVA F test, generally speaking, not very useful, right? Because you're making a comparison between these two models, i.e., is your model useful? But there are some settings that the ANOVA F test is useful, and we'll explore that in Module 5. So it's not entirely not useful. So that's the ANOVA F test. The t-test tests whether an individual coefficient is 0. So in words, what this means is that we can drop predictor x sub j from the model, and this part here is a key in the presence of the other predictors. So you must leave the others in. That means when you have the others, can I drop x sub j? And the alternative, again, we cannot drop the predictor in the presence of the other predictors. So an insignificant t-test indicates that that predictor x sub j can be removed from the model and you leave the others in. That predictor is not needed in the presence of the others. Now, if x sub j is highly correlated with at least one of the other predictors, or is a linear combination of a number of other predictors, that predictor x sub j will be insignificant, as the addition of that predictor doesn't help in improving the model. Right? So a very common misinterpretation people will have is, oh, if we fail to reject the null, we can drop x sub j and we say x sub j is not useful in predicting the response. Well, it is not useful in the presence of the others, but on its own, it still could be useful, right? X sub j itself may still be linearly related to the response. If your goal is to assess just simply if x sub j is linearly related to the response, then you only need to use a simple linear regression, right? So just be aware the difference in interpretation for the t-test, right, is that that predictor is not useful in the presence of the others. On its own, it may still be useful. So that's a key distinction to be aware of. So just a quick summary about goals and purposes of simple and multiple linear regression. So simple linear regression, scatter plots, correlation, they all explore the relationship between two variables, and only those two variables, without taking into account the impact of other variables. With multiple linear regression, we're exploring the relationship between the response variable and multiple predictors simultaneously, right? So you just have to be aware what your goals are and what you really want to do before deciding whether you want to put multiple predictors in, right? Because we could improve the model, right, in terms of predicting the response, right? We could include more useful predictors, right, into the model to improve the prediction. But if your goal is only to explore relationship between two variables, then you're really in the simple linear regression framework.